Hello and welcome to this video titled IP Precedence and DSCP. In this video we're going to dig a little bit deeper into the IP version 4 TOS byte, sometimes called the differentiated services field. I'm going to define DSCP and show you how to understand it and count in DSCP, and we're going to look at some common DSCP per hop behavior classes. So let's start with the IP version 4 TOS byte. Like I mentioned, depending on some newer papers you might read, this byte might also be called the differentiated services field. And let's just refresh ourselves real quickly here with where this is. So this is what we're talking about right now. So we are looking at this byte. Okay, so we're going to dig into the details of that right there. Okay, so originally, back in RFC 791, which first defines the IP packet, the header format, and what all those fields mean, this is what they originally defined that byte to mean. So they said that, so this is the entire byte right there. They said that bits 0 through 2, it's kind of interesting they count starting at 0, but these first 3 bits right here were the IP precedence bits. And this was used to define the priority of traffic. So routine traffic, or pretty much the default traffic, is all zeros. And that's every packet your laptop or PC spits out will by default be categorized as routine with 000. Now with 3 bits you could go all the way up to the number 7, an IP precedence of 7, and each one of these had a special name or label that you can see from that. Now these other bits, for example, this here normally was a 0, but if you set that bit to a 1, that meant that this packet was requesting a path through the network with the lowest delay possible. If you set the next bit to a 1, that meant you were requesting the highest throughput possible. The next bit, if you set that bit to a 1, meant you were asking for the highest reliability, and then the last 2 bits did not have any meaning. Those were reserved for future use. Now what's kind of interesting is that even though these bit meanings were set decades ago, and quality of service features have been out for decades, vast majority of network vendor equipment never bothered to look at these bits right here. So even if you had a host device like a server or a PC or a laptop that was capable of setting the delay, throughput, or reliability bits, you were wasting your time, because most routers and switches, like 99.99% of them, didn't even look at those bits, didn't even have the capability to look at those bits with any QoS features. So for the longest time, when we talked about doing IP, or when we talked about doing quality of service at layer 3, all it meant was dealing with the precedence bits. And you could see here, you had a choice of 8 different levels, from 0, which is routine, up to the highest, which was 7 for network control. And technically speaking, the values of 6 and 7, you weren't really supposed to use those. Routing protocols could use those. For example, OSPF LSA's link state updates go out with an IP precedence of 6, inter-network control. So really, as an end user with a server or a laptop or a PC, the only values you could really set were from 0 to 5 for IP precedence. So if you think about all the different kinds of traffic that's flowing through a network, there's a lot more than 5 different levels of traffic, but with the original way of IP precedence, that was it. Every flow of traffic that was going through your network, you could only choose from 6 different levels here, 0 through 5, to categorize or classify that traffic. Then, a couple of decades ago, some people came around, they looked at this and they said, you know what? This is an 8-bit field here, but we're really only using 3 of those bits. The last 5 bits aren't being used. And yet, wouldn't it be nice if we could have a lot more different classes of traffic than just 6 levels? Wouldn't it be nice if we could have like dozens of levels of traffic using this exact same byte? And so they said, you know what? Let's repurpose that byte and look at it a slightly different way. In other words, let's interpret the bits a little bit differently. So now, when you enable QoS on a router or switch, and you want the router or switch to look at this octet, this byte, you have a choice. You could have it look at the old way, which is IP precedence, which means it's only going to look at those 3 bits there on the end and that's it. Or you could have it look at it the new way, which is called differentiated services code point, or DSCP. DSCP now looks at the first 6 bits of that byte to identify the relative priority of the packet. And this is both for IPv4 and IPv6. So for IPv4 and IPv6, they both had a 1 byte field. Now IPv6, it's just supposed to be DSCP. With IPv4, you could do the older way of IP precedence or this. So how does this work? All right, so here was the old way, right? The legacy way of IP precedence, where the first 3 bits here in yellow, the priority bits, were all you could really look at. With DSCP, we now have the first 6 bits. But technically speaking, it's really 5, not 6. So for this, I'm going to do a little bit of whiteboarding right here. So I want you to notice that the first 3 bits, which we used to call the IP precedence bits, those have a different term now. We call those the class selector bits. And the next 2 bits are called the assured forwarding bits. All right, so let's break that down a little bit here. And actually, I'm going to, I'll just go ahead and do that here on the whiteboard. So when you are, and the purpose of this whole video course here is not to show you how to configure QoS features, but just to give you like a high-level overview. But part of configuring QoS is you would say, when packets come in that match this particular criteria, like maybe they're voice packets or they're video packets, I want to go into this byte and I want to set the DSCP bits. Okay, now when you're configuring it, when you tell it you want to set the DSCP bits, you're going to have some options here. One way is you could do it like this. So here's our toss byte, the entire byte. All right, here's the entire 8 bits, and we know that DSCP is dealing with 6 of those bits. If I've done my counting right, I think I've done it. Yes, right there. Okay, so with 6 bits, the way you do the counting, normally people, when they're first learning about DSCP, the first thing they get wrong is when they think about counting in binary, they say, okay, that's the 1 bit, that's the 2 bit, 4 bit, 8 bit. No, that is wrong. So when it comes to DSCP, those last 2 bits, these right here, are not used for the prioritization of traffic. They actually do have a meaning. They're called the explicit congestion notification bits, but that has nothing to do with the relative priority of this traffic. So because they're not part of the priority, the bit counting starts right here. 1, 2, 4, 8, 16, 32. So because the counting starts right there, you can see that just providing a simple DSCP number, your lowest number could be 0, which would be all those bits zeroed out. Now if I set all those bits to a 1, what would that number be? The highest number is 63. That's the highest number. If I count these up, 32 plus 16 plus 8 all the way down to 1, that's your highest value of 63. So when you do get around to learning how to configure QoS, if you identify traffic as belonging to a particular class that you're interested in, whatever that class is, telnet traffic, voice traffic, low delay traffic, whatever you want the class to be, and then once you decide, okay, now that I've identified that, I want to mark the DSCP bits. You could do this. You could say, I want to mark that class of traffic as DSCP 42, or DSCP 12, or DSCP 63. You got any number there between 0 and 63. And then once you've marked it, now other QoS features could be looking for that marking. You could have other QoS features that say, okay, when I see a packet that comes in with a DSCP value of 49, I'm going to do this special thing to it. Versus something else that's got a DSCP value of 22, I'm going to do something else with that. Okay, so that's one way you could mark the DSCP bits, is just by picking a number between 0 and 63. Now, there's another couple ways you could do this here, and I just want to show this to you. All right, so let's jump into a router here. Don't worry if you don't understand all the commands I'm doing here. That's not the intent. We'll just say match any. Okay, policy map test. Okay, so notice here, don't worry about everything I've done up to this point, but right now I'm saying, okay, if stuff matches a certain criteria, I want to change the DSCP bits. So notice my options here. I could pick a number between 0 and 63, and hopefully now you understand why it has this range from 0 to 63. Or I could pick some of this stuff. Now what the heck is that referring to? Well, that gets us into our next slide, which are DSCP per hop behavior classes. Now let me step back here for a moment and define this term PHB, or per hop behavior. So in the sort of broad world of quality of service, each networking device, whether it be a router, a switch, a firewall, even a Wi-Fi access point, any networking device that has the ability to have quality of service turned on and do something special from a QoS perspective is called a hop, right? That's a hop of QoS. So your packet, as it's going from source to destination, could go through, a dozen different hops of various routers and switches and things, all of which could act on that packet with various different quality of service features. So when we talk about per hop behaviors, that's just a fancy way of saying on every given device, once it hits that hop, what behavior is that hop going to do? Is the behavior of that hop going to be set the DSCP bits? Is the behavior of that hop going to be slow down or speed up that packet? There's a whole bunch of things QoS could do at that particular hop in the network as a behavior for that packet. So that's what PHB, or per hop behavior, means. It sounds fancy, but it's nothing really that complex. Okay, so as this mentions here, there are 4 high-level traffic classes defined for DSCP per hop behaviors. And this is just terminology, but I want you to understand what these mean. So first of all, there's something called default forwarding, or DH. All that means is that you're not really doing anything with the DSCP bits. You're just leaving them as all zeros. So when the packets pop out of your laptop or a PC, they're using this traffic class called the default forwarding traffic class, which means your packets are treated the same way as everybody else because they're all zeros. So that's the default forwarding per hop behavior. Now the opposite extreme of this is expedited forwarding. So for example, any IP phone you've ever dealt with, if you've ever worked with a Cisco IP phone or an Avaya IP phone or whatever, and you pick it up and you start talking, one of the things that IP phone does is, like the name infers, it takes your voice and digitizes it into an IP packet. Well, part of that process, we know it's got to append an IP header, which has got a toss byte in there. Every IP phone, when it deals with that toss byte, it will set the DSCP bits to expedited forwarding. So expedited forwarding is kind of the well-known DSCP value for voice. Now, it doesn't mean that other things can't use it. You could set anything you want to expedited forwarding, but just know that that's typically what voice is assigned to, is expedited forwarding. And this is how the DSCP bits are allocated for that. So notice it's the 6 bits on the end. Those are our DSCP bits. And once again, if you count the binary starting with this number right there, you're going to get screwed up. And you're going to wonder, what the heck is 46? This doesn't add up to 46, but if you count the binary starting, oops, not there, if I can line up my pen, right here, with that being the 1-bit, 2-bit, 4-bit, and so on and so forth, 1, 2, 4, 8, 16, 32, well, now you can see when you add them up, you've got the 32-bit turned on plus the 8-bit, which is 40, plus 4 plus 2. So that's the same thing as a DSCP of 46. So if I go back into my router here, you can see, oops, right here, if I set the DSCP to the number 46, that would be the exact same thing as setting it to expedited forwarding. So I have a choice. I can set to EF or the number 46. Most people don't normally select 46. They normally select EF. So EF is sort of the well-known DSCP group for voice. And you can see here it's giving you what those first 6 bits are. All right, so far we've talked about the low end, which is default, all zeros. We've talked about sort of the upper extreme, which is expedited forwarding. Now, what are the categories in between there? Well, there is assured forwarding. Assured forwarding AF11 through AF43. Let me go back to the whiteboard here to explain this a little bit. All right, so here is my toss byte. Okay, and we know that within the toss byte, only these 6 bits here are used for DSCP. Remember, these are for explicit congestion notification, has nothing to do with the priority of a packet. Okay, so these assured forwarding classes, how do they work? All right, so first of all, we know that with AF, it's going to be AF1 through AF1 something. It's always a 2-digit number. AF1 something through AF4 something. Let's talk about this first number. That first number directly maps to your IP precedence bits. You remember what those bits were? Those bits were these 3 bits right here. Those were your IP precedence bits. So if I have AF1 something, that means that. That's the value of 1. If I have AF3 something, it's that. And if I have AF4 something, it's that. So let's start out with the AF1s. Okay, so as far as packets are concerned, I'm just going to do a couple of them here. So let's say AF1 something, AF2 something, and AF3 something. All right, so if, let's say I'm an interface on a router, and I have a bunch of packets to transmit, so many packets to transmit, I can't get them out on the wire fast enough. So behind me, I've got some memory, I have some memory queues, and packets are filling up in those queues, and I need to transmit them out on the wire. All right, if I am QoS aware, and I'm looking at DSCP, and I see this, so in my buffer, I see some AF1 somethings, 2 somethings, and 3 somethings, just like with IP precedence. With IP precedence, the higher the number, the higher the priority of the packet. So if I'm doing QoS correctly, I should pull my AF3s, put them on the wire first, before I get to my AF2s and my AF1s. Okay, because those numbers, 3, 2, 1, they map directly to the IP precedence bits. Now what about the second number? What the heck does that stand for? All right, so that maps directly to these 2 bits right here. Now, that second number is always going to be some value between 1 and 3. Not 0. It's not going to be 0. It'll be 1 and 3. So, for example, AF22, and this is called an assured forwarding. That's what AF stands for, an assured forwarding class. AF22 means I've got the value of 2 encoded there. There's 2. And I got the value of 2 encoded here. Because remember, if we take a look at each one of these boxes separately, you start counting 1, 2 in binary. You start counting 1, 2, 4 in binary. Each box is looked at independently when you're talking about AF. So that would be AF22. I've got a 2 encoded in these 3 bits, and I've got a 2 encoded in those 2 bits right there. All right, let's take a look at another value. Okay, what if I had AF31? Well, that means we encode the number 3 right here. Those are my class selector bits. And these right here are my assured forwarding bits. So I have the number 1 right there. That is AF31. Now you say, well, Keith, okay, but if I have 2 bits, technically I have 4 possible combinations. Let's just delete all this stuff. If I have 2 bits, I could start with that. I could go with that, and with that. So certainly, this is my values of 1 through 3, but what about 0? You know, isn't there an AF30 or an AF20? Well, let's go back to our router here for a second and take a look at him. Notice, there's no zeros, are there? When it comes to assured forwarding, it's always 1, 2, or 3. And here we actually see the combination, right? Here is AF1, and there's 1. Here's AF1, and here's 3. But there's no AF10 or AF30. What is that? So when these 2 bits right here, when these assured forwarding bits, when the assured forwarding bits are zeroed out, that's known as a CS value. A CS value. So for example, okay, so if I have this, what that would represent is my class selector bits are 4, my assured forwarding bits are 2, so that would map right here to AF42. However, if I have this, my class selector bits are still 4, but because my AF bits are zeroed out, that simply matches to CS4, as we see right there. So whenever the assured forwarding bits are zeroed out, this is a class selector value. And you might say, well, why did they call it a different name? Why didn't they just keep everything as AF? Well, I can only speculate, but my speculation is this, is that when you have a CS value, you're doing that because you want to be backwards compatible with IP precedence. So for example, if I had router 1 right here and router 2 right here, let's say router 2 is super, super old and his code doesn't even support DSCP. All he supports is IP precedence and that's it. So all he can look at are the 3 first bits in the toss byte. The other bits he can't even pay attention to. This guy here can do both DSCP and IP precedence. And I decide, well, hey, if I'm on a device that can do DSCP, I want to do DSCP. I want to stay away from IP precedence if at all possible. Okay? Well, if this guy does DSCP, if I set it to one of these values, if some packet comes in that's voice or telnet or web browsing or whatever, so here comes a packet, and I decide, okay, I want to go into the toss byte and I want to change the DSCP bits. If I set to one of these values right here, and then I forward that packet on to router 2 is just going to ignore my AF bits. Once again, the first 3 bits were called the CS bits, the next 2 bits were called the AF bits, and then the last 3 bits weren't really used in this scheme. Well, he's going to ignore the AF bits because he doesn't even look at that. So in order to be backwards compatible, I might as well just mark the 3 bits only on the front end, and with DSCP, when you do that, we say you're using a CS value. And notice you can go from CS1 all the way to CS7. But remember, word of warning here, CS6 and CS7, you're really not supposed to use that because that's the same as IP precedence 6 and 7. And those were used for like network control and inter-network control for like routing protocols. So I'm going to give you some bits in binary, some binary combinations. I'm just going to use this black surface here as my whiteboard. And I want you to pause the video for just a couple seconds and identify what CS or AF value those bits correspond to. So here we go. 1, 2, 3, 4, 5, 6, 7, 8. And by the way, I might throw some intentional errors at you as a gotcha that doesn't really map to anything. And I want you to tell me that if it doesn't map to anything. So here we go. Let's do this first one here. All right, what CS or DSCP value does that map to? Go ahead and pause the video and then press play when you think you've got the answer. All right, so hopefully you said that maps to AF33 because your class selector bits, in this case, are equaling 3, and your assured forwarding bits are also equaling 3. Good job if you got that. Let's do another one. Oops, make that a little bit bigger. Okay, so here's your next one. Press play once you think you have the answer. Hopefully for that, you said that is assured forwarding 41. Class selector is set to a 4. Assured forwarding bits are set to a 1. That's AF41. Let's do another one. All right, what about this? Press play when you think you have the answer. Okay, so this was a trick question. You may have said, oh, well, that must be AF51. Well, it's not, because remember, your AF values don't go that high. Remember, your AF only goes up to 43. Anything above that, and you're out of scope when it comes to AF. So if I actually gave you that number, let's go back to that. Actually, let's go back to my whiteboard here. So if I said 101, 01, 000, okay, and you said that was AF51, well, we know now that AF51 doesn't exist. So if I actually wanted to set that number in my packet, so if a packet came in, I said, oh, that is telnet, that's voice, and I want to give it that binary pattern right there. Since I can't choose AF51, what would I choose? I'd have to choose a plain old DSCP value. I'd have to say, okay, well, these here are my ECN bits, those don't count. I'd have to start adding it up. That's the 1-bit, the 2-bit, 4-bit, 8-bit, 16, 32. Okay, so the 32-bit is turned on, the 8-bit's turned on, and the 2-bit's turned on, so that's 42. So I would simply say that is DSCP 42. That's how I would get that number put into the packet, is just by typing in DSCP 42. That's what we saw up here. I would do set IP DSCP, and instead of saying AF or CF, I would just put in a number, 42, and that would give me that value. All right, so that concludes this video on how IP precedence and DSCP bits work. Thank you for watching.